begin for today. Sorry, the stuff on the right, ignore, that's left over from calculus. Just FYI. So, let's see, last time we finished by talking about lists, right? So we were talking about lists and we were counting the number of different types of lists that you could make. And if I gave you a k element list, so a list of k elements, and you had n options for each element, and we allowed repeats, then the number of lists you could make was n to the k, right? So if I say, how many 3-element lists could you make if you had 4 options for each of those? Then the answer was 4 cubed. 4 options for this, and for each of those 4 options you have 4 options for this, and for each of those 16 options you have 4 options for this. For a total of 64 options, right? So we have that way of counting lists when we allowed repeats. And then we have this other notation, n sub k, which is the amount of k element lists you can make when you have n items to choose from without repeats. Right? You remember that? The number of k element lists we can make with n choices and no repeats. So the example we did for that, I don't remember exactly what it was, but it was something along the lines of, we're given that 10 people are in a club. How many ways can we elect a president, a vice president, a treasurer, and a secretary from the club? And the answer was 10 sub 4. In other words, we had 10 options for the president, but once our president's selected, we now only have 9 options for the vice president, because someone can't be a president and a vice president, right? And once you had your president and your vice president, now there's only 8 left to pick for your treasurer and 7 left to pick for your secretary. Does that make sense? So this is how we calculated it without repeats, and then n to the k is how we calculated it with repeats. We're going to focus for this section on the without repeats list. So anything about this example that doesn't make sense, anything we need to recap, anything feel fuzzy? We're perfectly solid with this, ready to go? Yeah. Okay, so then what we're going to move on in this section, what we're going to be most interested in, title section, factorial, is factorials. And you probably come across factorials before. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is 10 factorial. Well, we're going to have n factorial defined in this way. It's how many n element lists you can make when you have n options to choose from. Right? So n sub n. So we start at n and we keep going until we get to n minus k plus 1. If n and k are the same thing, then n minus n plus 1 is n minus n plus 1 is 1. So we start at n and we go to 1. Remember, that's what this definition says. Right. N sub k, start at n, and go until you get to n minus k plus 1. Well, if k is n, then that start at n and go to n minus n is 0 plus 1 is 1. So that's what we mean by n factorial. So there's 4 people in this room. If we were to ask ourselves, we started a club and we're going to elect a president, vice president, treasurer, and secretary. How many ways could we do that? The answer is 4 factorial. We have 4 options for the president, and 3 options for the vice president, and 2 for the treasurer, and 1 for the secretary. 4 factorial. So that's the question that we want factorial to answer. We want it to answer this question except for when we put n in there. Number of n element lists we can make with n choices and no repeats. That's what we want factorial to capture the count of. Remember, we're still interested in counting. The overall, so these are section headers. The overall header is counting. And we've been talking about different ways to count things. This counted the number of lists like this. We want factorial to count the number of n element lists I can make with n options, no repeats. Does that make sense? So, quick example, 5 factorial, what is that? That's 5 times 4 times 3 times 2 times 1. That's how many 5-element lists we can make if we had 5 options. We have 5 options for the first, and 4 for the second, 3 for the third, 2 for the fourth, and 1 for the last. Right? And that comes out to 120. So now let's move on to a weird case. What about 0 factorial? What should 0 factorial be? What's 1 factorial?
1.
Okay, so what should 0 factorial be?
0.
So let's ask it in terms of our question. So how many 0-element lists can we make with 0 elements to choose from, no repeats? The answer is 1 list. It's this list right here. It's the empty list. How many items are in that list?
0.
0. How many items did I choose from for each of my options?
0.
0. So there's one way to make that list. And it's that list right there. It's the empty list.
That is so not even cool.
I think it's cool.
No. Okay, so what's the definition of factorial?
What's the definition of factorial? It's right here.
No, that's n factorial. What does the factorial do? It basically just counts down from the number.
This is the exact definition of it. The symbol, so when you have a number factorial, because factorial is an operation on a number.
Right, that's what it
So it needs to come with a number.
What does it do?
So a number factorial is starting from that number, multiplying by decrementing 1 all the way down to 1. Now, that didn't capture the special case of 0 factorial. So now we're going to come up with what's called a recursive definition for factorial with the 0 factorial in mind. But you should already have intuition for what factorial is. The only case that should have seemed weird to your mind is, what about 0 factorial? And then we don't go into negatives when defining factorial. So, here's our recursive definition for factorial. N factorial equals n times n minus 1 factorial, where 0 factorial is 1. Good with that?
Yeah.
So using that definition, if we were to say what is 5 factorial, that's equal to 5 times 4 factorial. But what's 4 factorial equal to? That's 5 times 4 times 3 factorial. Right? And then what's 3 factorial equal to? And you keep going until you got 5 times 4 times 3 times 2 times 1 times 0 factorial. And then we define 0 factorial to be 1.
Right.
So that's what we call a recursive definition. Recursive meaning that you keep applying the definition over and over again until you get to this base case. Right?
Right.
So what was 5 factorial? 5 factorial is 5 times 5 minus 1 was 4 factorial. So 5 factorial is 5 times 4 factorial. Okay, that begs the question, what's 4 factorial?
Right.
Well, that's 4 times 4 minus 1 is 3 factorial. And you keep applying the definition over and over again until you get to this point, and then you apply it one more time to plug in 0 factorial, actually no, it's just 1. So does that make sense? And this is only defined on natural numbers. We don't ask what's 6.5 factorial.
Why is that?
You define your operations on sets of numbers. You do that in general. For example, when you're just talking about the set of natural numbers, we don't have a notion of division defined. What's 6 divided by 7 in the natural numbers? That operation doesn't make sense unless we're talking about rationals. Does that make sense?
Okay. So
I mean, here's a good way, probably not a bad side note to take. That actually raises a great question, because this comes up over and over again in your education. You just don't remember that it didn't. So, think about some 3rd grade kid, and they just learned division for the first time, right? And you can go and you can ask them questions like, what's 6 divided by 2? And they can answer, and they can say, oh, that's 3. But then you go and you ask the kid, okay, what's 7 divided by 2? And they say, no, it doesn't work. You say, sure it does. 7 halves. What? No, you didn't do anything. You just did 7 divided by 2. And so you try to convince the kid that this is a perfectly good number. You get a little bit older, and we introduce you to the square root function. And I say, what's the square root of 4? And you say, oh, I don't have a problem with that. That's 2. I say, okay, what's the square root of 2? And there came a point in your education where you were like, you can't do it. We say, sure we can. It's just the square root of 2. And you say, no, you're cheating. You didn't really do anything. No, that's a perfectly good number. Right? And then you eventually get comfortable with that, and then someone comes along and they say, okay, what's the square root of -1?
Right.
And once again, you say, no, you can't do it. There's no way to do it. We say, sure we can. We just call it I. And they say, well, what's I? Oh, it's a square root of -1. You didn't do anything. That's a perfectly good number.
Yeah.
Perfectly good number, perfectly good number, perfectly good number.
Right.
It just means that we changed the numbers that we allow to be answers. Right? Here, we had to start allowing fractions to be the answer to the question. Here, we had to start allowing irrationals to be the answer to the question. Here, we had to allow complex numbers to start being the answer to the question.
Okay, but think about it. If we needed that to prove something, wouldn't that be false? Like
Every one of these statements are equally
right,
valid.
like who would come up with I? They would
So-
come up with it to prove something, right? To prove a statement, to prove whatever. They wouldn't just come up with it.
Well, here's what, it's not that they, so you come along and you say, what if I let this be a real, what if I let that number exist? And then let's see what else happens. And you say that's bullcrap, but this has happened all through history.
Yeah, I guess.
You go and you
if
tell the
have
Greeks
no-
about the number 0, and they say 0, no, that's not a number. If you're going to have something of something, you got to have something of something. You can't have 0 of it. Don't give me that nonsense. Show me something that's a length 0. No, you can't do it. Don't pretend that that's a number. And so they rejected 0. And they had a problem with 0. And it took the Hindus to finally introduce the number 0 into our mathematics. And the same thing has gone on with all these. And that rejection is actually the reason why we call these imaginary numbers. Because when they first came up, the community wanted to reject them. But no, they're very useful, practical numbers that help us solve lots of problems. Just like any other number. So, side note. So we pick the domain that we want things to be defined on. We pick the numbers that we want answers to. When I'm talking to a kid, I don't want them to get this as the answer to something. I want it to be like this. And then when I'm working with kids who are first getting introduced to this, here's how we do it. So it's just a matter of how you want to have meaning. And there's ways to extend definitions to other numbers as you go further along in mathematics, and we find ways to do that. But usually introducing something, the best way to do it is with the natural numbers. Good, simple set of numbers to start with. Okay. I don't think that we didn't finish all this. Okay, so we talked about 0 factorial equals 1, and I think that makes good intuitive sense to all of you why it does. Talked about this, so now let's talk about product notation. Product notation, this is notation to write something shorthand. So here's what it looks like. So that's a capital Pi symbol, in case you can't read my handwriting. At the bottom, we have some dummy variable, in this case it's k. The dummy variable tells us where to start and what we're substituting in for, and n tells us where to end. So we'll come back to the definition after seeing an example, because then I think it'll click in your head. So example, if you come across this is saying the product of all k starting at k equals 1 and going to 5. Okay?
It's integers, right?
The product of all k is k starting at 1 going to 5. Yeah, it increments by 1 from whatever this number is to whatever that number is. So that is shorthand for 1 times 2 times 3 times 4 times 5. That make sense? So when I say the product from k starting at 1 to n of k, that's equal to 1 times 2 times 3 all the way up to n, which is the same thing as n factorial. Let's look at another example that's a little bit more complex. So here, notice where we start, k equals 3. We're going to 6, and now we're plugging into 2k plus 1. So when I plug in 3 for k, what do I get?
6.
7. 2 times 3 plus 1, 7, right? So we get 7. Now plug in 4 for k, what do I get?
9.
Plug in 5 for k, what do I get?
11.
Plug in 6 for k, what do I get?
13.
And then stop, because this tells me where to stop. So this tells me where to start, keep incrementing by 1 until I get to here, plugging into this, multiplying all your answers together. So this is shorthand for this right here.
Right.
Wait, what? That makes sense.
So
but
what do you use product notation for?
It's an easy way to represent, well, it's shorthand for doing this. I mean, this doesn't seem useful for representing these numbers, but
For long numbers, what?
maybe I want to talk about, you know, the product of all the numbers from 1 to 1,000. And continue on my merry way. To have another way of writing that out, how else would I write that out? Would I write 1,000 times 999 times 998, hope you get the pattern, dot, 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 times 2 times 1.
Right.
So it's just notation. It's shorthand notation to save you from having to write a lot. And it's going to become very useful as you continue in this class, so it's nice to have. And the authors need to use it as well. So it's just notation. Understand what it represents. If you have questions, then let's go over the questions. And then let's go over one more rare case using this notation. So if I take the product of all the numbers starting at 1 and going to 0 of k.
Okay, that's not an 11, is it?
What?
Under the number.
That's pi.
You're saying this?
That's why I was saying.
This is a capital pi, sorry.
Okay,
Capital pi.
so,
That's 11. That's always capital pi.
So, how would you can't really have a case that starts at a number and then goes to a lesser number, can you?
Great question. In general, that could get in a bad case. That's why we specifically show this case, because this and this are the same thing.
Right.
But if I try to do something like the product of all the numbers from k equals 7 to 2, then yeah, we're in trouble.
Right.
We don't have a way to interpret that.
Right.
So here's the weirdest case that you're going to see using this product notation. In other words, here's as crazy as it's going to get. In general, you'll see it like this or like this. That make sense? That's the end of the first section on factorial. So any questions about anything?
yeah, is there a certain way to find solve the equation n factorial equals 720?
Oh, yeah, so let's look at an example like that. So let's look at, we want to figure out what n is if we know that n factorial equals 720. How do we take on this type of problem now? Well, there's a couple ways that you can take it on. You can flat out, try plugging in 8, maybe that gets too big. Try 7, maybe that gets too big. You can flat out start multiplying.
Yeah.
What's 1 times 2 times 3, see when you
Right.
get 720.
But I was just wondering if there's a certain way.
There's no specific way to do it. You can also view it as n times n minus 1 times n minus 2. No, that's not going to help you. What's another way that you could quickly take that on? Yeah, I don't know. I think the best way to do it is to just start at 1 and see when you get there.
Another question.
What?
So you go until you get to the number that's on top of pi.
For here? Yeah.
So why do we go to 13?
No. Sorry, we keep plugging in k's until we plug in that number.
Until
So we plugged
say
in 3 for k,
plug
which
in
was 7.
6 for k.
We plug in 4 for k, we plug in 5 for k, we plug in 6 for k, and then we stop.
So it's only
This is the
gonna
biggest
be
value
that
we plug in
number
for k.
when k equals 1.
Huh?
When k equals 1, it's only going to be the number on top.
No, if k equals 1, that means you start by
I'm
plugging
saying
in
for
1.
that one. Just k, and k.
For this one? For this one?
Yeah.
So this, we start k at 1, and we keep going until we get to 5. So 1 times 2 times 3 times 4 times 5.
Right. That's what I'm saying.
Sure. And if this had been a squared, then that would be squared, 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 squared.
Mm-hmm.
Okay. Alright. So now let's start talking about sets. Sets are a pretty basic mathematical object. I don't know if we've already talked about sets in this class before. It's pretty typical that I bring it up before the book does, but sets. So we don't have a definition for what a set is, because a definition is a set is an undefined mathematical object. You have to start with undefined things to start giving definitions meaning. But the way that I try to give students intuition for what a set is I say a set is an unordered, unique collection of objects. An unordered, unique collection of objects. What do I mean by that? I mean that order doesn't matter in sets. In other words, these two sets are equal. And repetitions don't matter in sets. In other words, these two sets are equal. So all three of these sets are equal. Doesn't matter what the order is. Doesn't matter if it has repeating elements. All those sets are equal. You feel like you got intuition for what we mean by set? Mm-hmm. And we typically use curly braces to represent a set with the objects comma separated in between.
So integers would be a list then?
No, the integers are a set.
They're a set. Which I thought they were a set, but that doesn't make sense, because doesn't the order matter?
No.
Or repetitions?
So
no,
we haven't defined union yet.
That makes sense, I guess.
But yeah, the integers are just a set. They're the set of all the number that you know and love. All the positive, not all the positive, all the whole numbers are the integers.
So sorry to go back, but this was a question I had about multiplication. Why can't you, or factorials, why can't you have a negative factorial?
So imagine we use this definition for a second, which is a really common one. So let's say I have negative 1 factorial right here, right?
Okay.
Well, that's equal to negative 1 times negative 1 minus 1 factorial, which is negative 2. So I can't have negative 1 factorial without negative 2 factorial. And I can't have negative 2 factorial without negative 3. And that's an infinite regression. We start at 0 factorial and we work our way from there. So because you never hit the base case, you're never going to have it defined.
I see. So basically any negative factorial is undefined.
Yes. Okay. So back to sets. So we understand all three of these sets are equal. They're the exact same set. Right? Question.
Yes.
How many objects are in the set?
Yeah, but you have double objects. Cancel each other out.
How many objects are in the set?
That looks like 6.
6.
But I mean, there's
How many objects are in this set?
3.
And these are the same.
Yes.
Right.
How many are in this set?
It has to be 3.
Oh, 3.
3! It's the same set.
Right.
So repetitions don't count in sets.
No.
Repetitions don't matter. Order doesn't matter. So it's a unique, unordered collection is the way that a programmer would refer to a set.
Okay.
That make sense?
What was the case where it said, like, the order does matter?
That was in a list.
So is
The list 1, 2 is not the same thing as the list 2, 1.
Right, yeah.
Those are very different things, and you'll notice that we use lists to represent points. The point 1, 2 is not the same as a point 2, 1.
Right.
The reason we use lists to represent points is because we want the order to matter there. And we also want duplicates to matter. The point 1, 1, 2 is way different than the point 2, 1. Right? So when we want order and duplicates to matter, we use lists. When we don't want orders and duplicates to matter, we use sets.
Okay.
That make sense? Okay.
What's the notation?
Notation, introducing this notation in case we don't understand it.
Oh, okay.
So, this notation is a member of, is typically how we read it. So 5 is a member of this set. 5 is not a member of this set. Smiley face is a member of this set. The set containing 5 is a member of this set. So notice 5 is not a member of this set. The set containing 5 is a member of this set. What are the objects in this set? The set containing 1, 2, and the set containing 5. Those are the objects in this set. Maybe to pound the point home,
Yes.
How many objects are in this set?
3.
3 objects are in that set. And now we would say that the set containing 5 or 6
So the set
is now in there.
okay, so
Anything can be in a set, including other sets.
the set containing 5, 6. If you had something say the set containing 5 is not an element of the set containing 1, 2, and the set containing 5, 6.
Yeah, the set containing 5 is no longer an element of this set.
Okay.
That's nowhere in here. The set containing 5, 6 is in there, 2 is in there, the set containing 1's in there, and that's it. So now let's talk about sets being equal. How on earth am I going to prove that this set is equal to this set? How do we do that? The answer to that question is we show that everything in here is in here, and everything in here is in here. Right? Does that make sense? And once again, I can't stress this enough. If you read the book that we use, the author puts templates in there, proof templates for different basic types of proofs that you do, and he walks you through, using templates nice and slowly, how to do a proof of showing that 2 sets are equal to each other. So let's do a quick example of proving that 2 sets are equal to each other. So let's see what he wants to do. He wants to do the proof that E equal to the set of all integers such that x is even so that set we're going to call E. Prove that is equal to F, which is the set of all integers such that Z is equal to A plus B, where A and B are odd. So let's make sure that we understand what this is saying, then we'll go through the proof. Sorry, I really slanted as I wrote. So we've got set E, which is a set of all even numbers. And we've got set F, which is a set of all integers that can be expressed as the sum of 2 odd numbers. Okay? Do we feel like we understand what those 2 sets are? This is a set of all even numbers. This is a set of all integers that can be expressed as the sum of 2 odd numbers. Okay? Now let's prove that those are equal to each other. So we need to show that everything in here is in here, and everything in here is in here. So, 1, let E and F exist as defined up there. Good? So we've got our 2 sets. Now, I don't know, which one do you want to do first? Do we want to show everything in E's and F or everything in F's and E?
E's and F.
Show that E's and F. So we start with some random element in E. Let X be some random element in E. Pick some random element out of E. We need to show that's now an F. Okay? We'll pick a random element in E. We need to show that that's an F. If X is in E, what do we know about X?
It's an integer. It's an even integer.
It's an even integer. Then X is even. And so there exists some A such that, maybe we won't use A because that's what we use here. There exists some, what should we use? C such that X is equal to 2C. Right?
Okay.
That's what it means for X to be even. We can write it as 2 times some integer, right?
Does C need to be an integer?
Yeah. I'll stop writing an integer over and over again. Just so I don't get confusing notation. So, since X is even, then there must exist some integer c such that x equals 2 times c, right? Now remember what we're trying to get. We're trying to prove that x is in f. How do we show that x is in f?
We show that every element.
Those are both sets. Is that what you're saying?
X and f are sets. Not x and f, sorry. E and
Are
f.
sets.
Yeah. Don't let me screw up my language.
Okay, but x is even. Is that part of the set?
X is a set, or sorry, E is a set of all evens, right?
Okay.
That's what it is.
Okay.
Does that already confuse you?
Yeah.
Have you not seen this notation before?
No, but it makes sense.
Oh, sorry. Let's start with that notation first. So this is called set builder notation. So we do a dummy variable. It's the set of all something, and then we do such that, and then some condition. So let's think of an example real quick to help run this home. So what are the natural numbers?
1, 2, 3, 4, 5, 6.
0, 1, 2, 3, 4, 5, 6. In this class, the natural numbers start with 0. So we can say the set of natural numbers is the set of all x such that x is an integer and x is greater than or equal to 0.
Okay.
Okay? This is another way that we could define n. The natural numbers is a set of all x where x is an integer and x is greater than or equal to 0. A lot of the times we specify that x comes from some other set, and so instead of doing x such that x is in here, we often write just straight up, n is a set of all integers, is the way that we would read this, such that x is greater than or equal to 0. Same set. So n is equal to the set of all integers such that x is greater than or equal to 0. Okay. Sorry, I read that wrong. N is equal to the set of all integers x such that x is greater than or equal to 0. So here's another way that we could represent the natural numbers using set builder notation. Are you used to like intervals from algebra classes? Like if I said the interval from 1 to 3 on the real number line, is that not a good way to do this? If I say the interval from 0 to 1, is all these numbers? Okay, then that's not a good example to help. Trying to think of another example for set builder notation. Maybe you'll just get comfortable with it as we go. So now let's recapture what E is. E is a set of all integers x where x is even. So it's just another way of writing the even numbers.
Right.
So E is equal to, here's another way that we could write E, -4, -2, 0, 2, 4.
Why can't you just write
There's another way that we could write.
E equals brackets even numbers?
Even numbers?
Well, that's different than even integers.
Yeah, so even, so far we only have defined for integers.
What?
Is 2.4 even?
Well, yes,
So
right.
say even integers. That's not my point.
That's what this says. E is
So,
equal to
right,
the set
why
of all
can't you
integers
just
such
write-
that x is even.
Why can't you just write even integers?
You could, that communicates what you mean pretty clearly, but
So why make it so freaking complicated?
you think that this is complicated because your brain's not used to it.
Right.
As your brain gets used to it, there's going to be more complex thought that you can represent this way that's harder to capture with words.
Oh.
It's like algebraic symbols might be confusing to some kid, but there comes a point where those algebraic symbols really pay off. And you can
Yeah, I
write.
guess that's true.
So it's the same type of thing. It feels like it's messy the first time you see it, but as you train yourself to look at it, it helps you really quick understand exactly what set they're talking about. And you'll get to a point where your eyes kind of just skim over that and you already know what it's saying instead of having to read some sentence expressing.
Okay, what is the Z
What does it have?
again?
That is a set of all integers. So Z is equal to the set -2, -1, 0, 1, 2.
Is there another way to express that?
but you need to express them in terms of other sets. So in my calculus class,
So what's the first set you express it with?
so in the calculus class, we gave a definition for the natural numbers in terms of stuff that we'll come across later in this class, but then we say Z is equal to the set of all x such that x is a natural number, or x is equal to 0. In calculus, the natural numbers don't include 0. Different authors are different. Or negative x is a natural number. And that's how we define the integers in calculus. So let's make sense of this real quick. 17. Is 17 an integer? Well, let's see. Is 17 a natural number?
Yes.
Yes. Okay, so we're already good. It just needs to meet one of these conditions. 0. In my calculus class, 0 is not a natural number, but 0 is equal to 0.
Why is that?
Different authors use the symbol differently. There's not a good consensus about what the natural number should be. So some authors say, I don't care what you say, I'm going to use it this way. Other authors say, I don't care what you say, I'm going to use it this way. So at the start of every textbook, the author specifies how they're going to use that symbol.
And
So it's either all the positive whole numbers or all the positive whole numbers including 0.
so if you took negative 17 is not a set.
So now let's say negative 17. Is that an integer?
That makes sense.
Well, negative 17 is not natural. Negative 17 is not equal to 0. But what's negative 17? 17, which is natural. So this is another way that you can define the integers using this set of notation. So yeah, that's the actual definition that we use in our calculus class for the integers. So yeah, you don't have to use this messy way of defining it. It's just we didn't want to go through have a thorough definition for the natural number and work from there. Anyways,
Okay, I still don't understand how E is just even numbers.
that's what you read this. E is the set of all integers x. X is just a dummy variable, such that x is even.
See, that doesn't make sense.
It
Why
does.
doesn't that read x is in the set of integers such that x is even? I don't know. Not such that, but x is a member of a set.
Yeah, x is a member of the integers.
That means x is in a set.
Right.
X is even.
X is in the integers. X is even.
How does that make the whole set even?
E is equal to the set of all x, where x is an integer and x is even.
That makes 0 sense.
It does?
Yeah.
Let's think about this for a second. I say f of x equals x squared. And I say, what is that?
What do you mean?
Well, you've seen that before 100 times.
Okay.
And if I asked you to graph it, you would come along and you would say, oh, that's this thing right here.
Okay.
But what is this? This is shorthand for representing the infinite set of ordered pairs that satisfy that relation. So 1 comma 1's in there because 1 when you square it is 1. 1/2 comma a fourth is in there because 1/2 when you square it is a fourth. 2 comma 4 is in there. Negative 2 comma 4 is in there. There's infinite things in there, right? But this is shorthand for all the things that satisfy this relation. This is the set of all this such that the right-hand element thing is the square of the left-hand element thing. That's what that's shorthand for.
Right.
That's shorthand for this infinite set. So x is playing a dummy variable here, right? They're saying pick any real number and square it, and that's what the right-hand side is. This is saying pick any integer, and if it's even, then it's in the set. Kind of similar. I don't know if you see it. Does that not help at all?
Okay, but like, why do they freaking word it that way if that's...
I don't know what you mean by worded that way.
Why do they write it that way when that's not how it's worded?
E is equal to the set.
That's...
E
Okay, right.
equals the set, we're showing a set, of all integers x,
Okay.
such that x is even. It's a set of integers x such that x is even.
So, x is what's in the set.
There's infinite x's in it.
Right, I know.
Right.
Because x can be any even number.
X is every integer
X
that's also
is
even.
what's in there.
Huh?
Hmm.
That's just a dummy variable to represent what's in there.
Right.
It's like when I say f of x equals x squared, you say, okay, so you can plug x into that, but what else can you plug in? You can plug in any real number you want for x. X here is a dummy variable representing any integer. X here is a dummy variable representing any real number. Does that make sense?
Mm-hmm.
All right. So now we're getting more comfortable with set builder notation. Let's make sure we understand these two sets again. So E is equal to the set of all integers, x, such that x is even, or in other words, it's equal to all even integers. And F is equal to the set of all integers z, where z is equal to a plus b, and a plus b are odd. Another way of saying that is F is equal to the set of all integers that can be expressed as a sum of two odds.
Mm-hmm.
So, question, is 6 in here?
Yes.
How do you know 6 is in here?
3 and 3.
Because 3 plus 3 is 6, or 1 plus 5 is 6. There's infinite ways we could have added two numbers together to get 6.
Right.
But we just need to find one way to represent that. Okay. So, we have E and F, we're trying to prove that they're the same set. The way that we do that is we show everything in E is also in F, and then everything in F is also in E. So pick something in E and we call it X. This is not necessarily this isn't associated with this, it's just a variable. We're saying pick some random element in there. Good? So if X is in E, that means X is an even integer. That's what it means for X to be in E. E is a set of all even integers. If X is in E, then X is an even integer. Right?
Right.
And if X is an even integer, then there exists some other integer C such that X equals 2C. That's what it means for X to be even. Yeah? You guys are so unresponsive. You are the opposite of my calculus class. It's like you just don't say anything if you get it. But then what do you say if you don't get it? You still say nothing?
No, I asked a question.
I ask questions all the time. You just don't.
I just what? Say for the camera. Okay. So now we need to show that X is in F. How are we going to show that X is in F? We need to show that it can be expressed as a sum of two odd numbers.
Well, you can show that the sum of two odd numbers is even.
That's not the same thing. Showing that the sum of two odd numbers is even, showing that the sum of two odd numbers is in here. We need to show that something is even, it can be expressed as a sum of two odd numbers.
So you just do the opposite thing. You show that exactly what you just said. You show every even number is the sum of two odd numbers.
How? Okay, here's X. It's even.
Okay.
How do I show that's the sum of two odd numbers? What two odd numbers can I add together to get X? Like what? 3 and 5?
5.
When I add those together, do I get X?
Yeah.
I do?
8. It's even.
What if X is 105 or 106?
Doesn't matter.
It does matter. We need to figure out what two numbers we can add together to get this X.
We don't know what that X is.
I know, that's why we need a generic way to do it.
Oh, I see.
It represents any element. Pick some element in there. You need to tell me the formula I can use to find two integers that are odd, so that when they add together, they get X. Because whatever the process is that we outline, it needs to work for everything.
Okay, so what's the freaking formula? We're not gonna know.
You have to come up with that.
How? I know that X equals 2C. Is there a way that I can represent X as a sum of two odd numbers?
X equals 2b plus 1 plus 2b plus 1.
Then X equals, let's keep the variable we have, 2C plus 1.
Plus 2c plus 1.
Well, you added 1. What do you need to do to keep the equation true?
Plus 1. Wait, what?
Subtract 1. Now the equation is still true. X equals 2C, or X equals 2C plus 1 plus negative 1.
Yeah.
Right? And And let me rewrite it one more time, grouping my two terms together. So we have 2c plus 1, and we have plus negative 1.
Right.
Is 2c plus 1 odd?
Mm-hmm.
Our definition of an odd integer is 2 times something plus 1. Is negative 1 odd?
Yes.
Oh.
We could have rewritten negative 1 if we wanted to express it as an odd. What is it? It's 2 times negative 1 plus 1. There we go. That's our proof that negative 1's odd.
Okay, so that's what I said. So why can't you just go with that? Rudo?
No, you said A and B, which are variables that we don't have.
I did not.
Oh, you didn't?
No.
What did you say?
I said x equals 2c plus 1 plus 2c plus 1.
That's not the same thing.
That's not the same thing.
Why is that not? 'Cause
2c plus 1.
c is negative 1, which we could have plugged in.
X equals 2c.
Right.
It does not equal 2c plus 1 plus 2c plus 1. That would equal 2x plus 2.
2 times negative 1 plus 1 cancels out. No.
2 times negative 1.
That's brilliant. Okay.
Oh, you see it? I'm just proving that negative 1's odd. I just rewrote negative 1 in a way that we know for sure, okay, it's odd. This is a mini proof that negative 1's odd.
Mm-hmm.
So we have x equals an odd plus an odd. An odd plus an odd.
Uh-huh.
Therefore, x is in F. It's expressed as the sum of two odds. F is all the integers that can be expressed as the sum of two odds. X is all the even integers. Now, let me show you what I mean by this just gave us a generic formula for doing it for any x you want. Pick any even number. 72. So we got x equals 72. Well, then what does c equal?
36.
36. Then, you just barely said, x can be written as 2 times c plus 1, which is 73, plus negative 1.
There you go.
So you came up with the generic formula. Any x you pick, then this sum will always be your x. Right? Do you see the difference?
Would it be wrong if you did let x be 8? 3 plus 5 is 8.
All you did is prove that 8 is also in here.
Oh.
We need to show that everything in here is also in here.
Right.
Every x in E can be rewritten this way. X equals 2c plus 1 minus 1. Does that make sense? Make sure this clicks and ask questions if it doesn't, because once you see with this example, all the other examples we do proving sets are equal is just going to kind of fall out. It's the same process over and over again.
Well, looking at it to the proof, it just doesn't make sense, whereas 2 plus 2 and 2 is not odd, but it equals 4.
Okay, so let's go over it. You're saying let x be 4.
Right.
So if x equals 4, what does c equal? Okay, so then my proof is saying you can write x equals 2 times 2 is plus 1 is 5 plus negative 1. So 4 can be written as 5 plus negative 1. Therefore, 4 is also in this set.
Right, but well then it says where A and B are odd.
Right. A and B
Is
has
5 odd?
5 and negative 1.
Yes.
Yeah.
Z
Is negative 1 odd?
Okay.
So it can be expressed as a sum of two odd numbers. That's a good distinction to make. It's not saying that it can only be expressed as a sum of two odd numbers. Because you could have also expressed it as you could express it as c plus c, whatever c is, right? Which isn't what we did. Because c could be even or odd. So yeah, it's possible to express it as a sum of two evens in the case of 4, but that's not what we're saying. We're saying if it's even, then it can be expressed as a sum of two odds. There's two odd numbers that you can find out there, such that when you add them together, you get back your even. And this is a generic way to do it. We're saying whatever x is, pick x plus 1 and negative 1. Because x plus 1 is going to be odd, since x is even. But that's how we explicitly wrote that. Okay, so we showed anything in E is in F. Now we need to do vice versa. We need to pick something out of F and show it's in E. You with me? So then I'll pick Y out of F. What does it mean for Y to be in F?
It means that y equals a plus b where a and b are odd.
Yeah, it means that there must exist two odd integers, a and b, such that a plus b equals y. Right? Okay. So if y is in F, then that means that there must exist integers a and b such that y equals a plus b, and a and b are odd. Right? Okay, keep going with our definitions. What does it mean for a to be odd, and what does it mean for b to be odd?
It means that there has to exist, say, m and n such that
Then there exists m and n such that a equals 2m plus 1, and b equals 2n plus 1, right? Then add them all together. Then y, which is equal to a plus b, is equal to 2m plus 1 plus 2n plus 1 is equal to 2m plus 2n plus 2 is equal to 2 times m plus n plus 1. Here we go. Right? Therefore, 2 divides y, and y is even. Therefore, y is in E. So that's how you prove that two sets are equal. Show that every element in one set's in the other, and then every element in the other's in the one. If you kept track of what I meant by one in the other. All right. Next, we'll say subsets.
Is this the next?
No, it's still the same section. But we're in the second section.
I know.
Okay.
We have to do 3 today.
Yeah, and we're done with one. And well into the other. And we still have 2 hours. All the time in the world. Okay, we say
Are you staying after today?
yes, assuming students are here. But I'm going to do it up in that other room from here on out. You say that A is a subset of B, assuming A and B are sets, provided every element of A is in B. Notation is A is a subset of B. Okay.
so it's like a C with a line through.
Yeah, it's meant to mimic the less than or equal to symbol.
Yeah. So it isn't exactly less than equal to, it's just similar.
It's similar to it, it's not the same. Less than or equal to is defined for 2 numbers. This is a symbol defined for 2 sets. So let's see examples really quick. 1 1, 2, 3 is a subset of 1, 2, 3, 1/2. Everything in here is in here. Let's look at another example. The set 1, 2, 3 is a subset of the integers. Everything in here is an integer. What did I do last time? This.
Oh,
So make sure we understand the difference between subset and is an element of, because it's going to throw you off most likely as this class goes on. So 1, 2, 3 is a subset of this because 1's in there, 2's in there, 3's in there. Everything in here is in here.
but not the other way around.
Not the other way around. This is not a subset of this.
Right, okay.
1, 2, 3. The second thing 1, 2, 3 is a subset of integers. 1 is an integer, 2 is an integer, 3 is an integer. The second containing 5 is a subset of the set 5, 4, 3, 2. 5, 4, 3. 5 is in there. The set containing 5 is not a subset of this set.
It
What's
was
in
the
here?
set of the set of 5.
Yeah. So the set containing 5, what does it have in it? It has 5. Is 5 ever in this set? No, that's not 5. That's not 5. That's not 5. If I would have written it like this, the set containing the set containing 5, this is a subset of this set. Good? So question. If I tell you that A is a set, is A a subset of A?
Yeah. No.
No, A equals
They're
A.
equal.
What does it mean to be a subset?
That, well,
So here's a conversation that we're probably going to have a couple times as this year goes on. And we'll start now. Do not rely on your intuition.
yeah.
Go back to the definition, read exactly what it says, and see if it works with the definition.
That's funny. You've been telling us to literally use our intuition this whole time.
No, I said we will use your intuition because we have to start somewhere. So we use your intuition for what we meant by integers rather than formally defining them. But no, we do not want to rely on your intuition. We rely on the definition. So we say that A is a subset of B provided every element of A is in B. Is every element of A in A? Yes, then A is a subset of A. Here's another question. Have we already gone over the empty set?
Yes.
Well, yeah, over there.
That was the empty list. So,
Oh.
quick notation. This is shorthand for this. The empty set contains nothing. We use it over and over again, so we have this shorthand for it. So question, is the empty set a subset of A?
No.
Yeah.
We got a yeah, we got a no, you got to break the tie.
No.
No, right? Is everything in here in here?
No.
Yes, it is! Find one thing in here that's not in there. Just one.
You mean I was right?
You were right. Can you find a case where it's false? Is the statement false? No, it's not false. And it's true. So for any set you pick, the empty set is a subset of it.
Okay.
That makes sense?
Yeah.
Okay, perfect. So those are two weird cases that I thought are interesting for subsets.
Okay, hang on. So A.
These are both true statements. A is a subset of A, and the empty set's a subset of A, given that A is in the set.
So they can be subsets of each other? Why can't it just be like this?
I don't know what you mean.
Well, I mean, like, right here we're proving that they're equal to each other. why would we have one that's equal to each other now?
Well, in this case, A is equal to A, but A is also a subset of A. It's the same way that I say, is it true that 2 is less than or equal to 2?
Oh, okay,
Yeah. X is always less than or equal to X for any real number, right? You can say, well, it's also equal. Yeah, it is also equal, but
that makes sense.
that's true. So that is the counterpart to that. This doesn't really have a counterpart. So let's do another quick proof. I'll just get rid of some of these writing in this space. We're going to do a proof that X is in A if and only if the set containing X is a subset of A. So if A is a set, then X is in A if and only if the set containing X is a subset of A. Does the statement make sense?
The set of X is the subset of the set of A.
If X is in A, then the set containing X is a subset of A.
Is A not a set?
A is a set, X is just whatever.
Can you give us like an example of an application of this, and just to visualize it?
Okay. If 5 is in the set 1, 2, 5, then the set containing 5 is a subset of 1, 2, 5. Does that make sense?
Yeah.
Yeah.
And vice versa. It's an if and only if. We're
Hang
saying
on.
if this is true, then this is true, and if this is true, then this is true. Sorry, my symbols aren't straight. This
That's
is
all right.
in, and this is subset. You reading that okay?
Yeah.
Oh.
You're going to get confused by this notation. It's almost a given, so.
Okay.
We just got to see examples using it back and forth a lot to get comfortable with it. Okay, so we are showing that if this is true, then this is true. And then we're going to show that if this is true, then this is true. That's if and only if, right? We're showing this implies this, and this implies this. Okay? And when we're doing if and only if proofs, we typically draw an arrow off to the side to show which way we're going to prove first. So I'm going to show if this is true, then this is true. Good? 1. Let X be an element in A. Two. Then the set containing X is a subset of A since, I don't know how to say it, X is in A.
How else do, yeah, how
I don't know how else to explain it. It's a simple proof just to get you comfortable with the notation. So what does it mean for this to be a subset of this? Is everything in here in here? Yeah, everything in there, which is X, is in A. We're done. Now let's do it the other way.
It's kind of like using it to define itself, almost.
Let the set containing X be a subset of A. Then X is in A. That's what it means. Everything in that set is in there. X is in there. And we're done. I doubt the author has much of a longer proof than I do. Let's see how big his proof is. Yeah, he's a bit more verbose, but still. I think he has 4 sentences in all. So you want more words, you can read the author's proof, but I think you understand it. Nice simple proof to try and get you comfortable with that notation.
Why would they make us prove that? I don't understand.
It wasn't make you prove it. The author
What was
proved
the
it.
example?
And the reason that he proved it is to try and make it very clear what the difference between these notations are. I think is the point he's trying to hammer home.
The difference? That doesn't prove the difference. All I
Between
see is that they're the exact freaking.
this notation and this notation?
Yes.
This notation means X is in A.
Right.
This is subset notation.
They're not that far apart.
No, they're not that far apart. But that and that is different notation. 5 is an element of that set. The set containing 5 is a subset of that set. In other words, he doesn't want you to accidentally get confused this way.
Yeah.
The set containing 5 is not an element of that set. 5 is not a subset of that set. You see the big difference?
Yes.
That's why he's doing it, to make sure that when you use the notation,
Aren't those
Use it
kind of like
correctly.
nonsensical statements? Because 5 can't be a subset of anything because it's not a set.
5 is a set. Should we have this conversation real quick?
No.
Well, if it's not, I'm saying if it's just, I'm just a little confused because if,
So, set theory is at the foundation of all math. All mathematics comes back to sets. You can't get away from it. Every mathematical object is a set. Even lists are really special types of sets. And so 0, the actual definition of 0 is the empty set. The actual definition of 1 is the set containing 0, which is the set containing the empty set. The actual definition of 2 is the set containing 1 and 0.
wait, one second. I don't think that's not making a lot of sense to me. The 0 makes sense. I'm lost at 1.
1 is equal to the set containing 0. It's his definition.
Why?
Why does a word have a particular definition? It's what we choose for that symbol to mean.
Okay.
And it goes on. And all the natural numbers are defined in terms of sets. And then you can define what you mean by addition. And you can define what you mean by multiplication.
So what doesn't make sense to me is if 1 is
So 5
equal, if 1
equals
is
the set of
Containing 1, 0, 1, 2, 3, 4. 0 through 4, yep. That's what 5 is.
if 1 is equal to the set containing 0, then 1 is, like you just wrote, 1 is equal to the set containing the empty set. Doesn't that mean that makes it seem an awful like 1 equals 0?
No, the set containing the empty set is not the same thing as the empty set. Those are two different objects.
Because look, that is that, isn't it? That set contains the empty set.
Right? And we kind of hit that home when we were talking about this. The set containing 5 is not a subset of
So-
it. The set containing the set containing 5 is a subset of it.
Does that mean 3 is equal to the set containing 1, 2, and 5?
No, 3 is equal to the set containing 2, 1, and 0.
So what is equal to the set containing 1, 2, and 5?
The set containing 1 through 5. We don't have a shorthand for it. That's not a special set.
So really when you're adding and dividing and all your, not functions, what's it called?
Operations?
Yeah. You're really just,
Manipulating sets.
that's interesting, I never.
Everything comes back to set theory. And then that's what I mean by you have to start somewhere. We couldn't start with this definition for 0 and define the natural numbers and talk about what we mean by plus and talk about what we mean by
When
multiply.
2 is equal to the set containing 1 and 0, it's kind of like saying, sorry,
Yes, it's like
I
saying
don't
that.
understand it.
It's just a definition.
That's so weird.
Its definition, I get, I mean, the fact that it's a definition makes sense, but I don't understand how 2 is equal to that.
I don't know how to answer that question because
Do you understand what
Can
it is?
you give like an example of like how to apply that? I don't even know.
oh, you want to start defining operations, and you want to say, okay, so how do we define 2 plus 3 now when these are their definitions?
Well, I don't even understand how 2 is equal to that. I mean, because I guess you can't really.
Well, if you want to be explicit,
Confusing.
here's what 2 is. There's 2. Everything is defined in terms of sets.
Okay. So everything is defined in terms of.
That's why set is an undefined term in math. We don't have a definition for set. We use set to define everything.
Okay. So everything is basically defined in terms of the empty set. Everything.
In terms of sets.
So the empty set is 1.
Well, every set can be.
The empty set is 0. The set containing the empty set is 1. There's 1.
Right, so the empty
There's
set,
2.
the empty set.
And you can go on to make 3, 4,
The
5.
empty set to the power 2 is 1.
Well, we have to find to the power here.
So why do we equate those things? Why do we equate 1 with the set containing 0?
Because it turns out, based off of how we define our addition and our multiplication, that when you apply those operations the way they're defined, this set acts exactly the way we expect the number 1 to behave.
So can you give an example of that?
Not briefly, no. Because we have to define what all these things mean. Right? That's the place I wanted to start my calculus class with, but even in that class I decided not to go all the way that far back.
Maybe we should do
But
that
now,
next year.
since classes do go back that far,
I definitely want to.
well, that's actually what I want to do at the end of this year if we have time. It's what I intended to do last year if we had time, but we got bogged down and didn't have time to go through it. But I want to develop the natural numbers with you guys at the very end of the year if there's time, and go through that exact stuff.
At the beginning.
Because there's more important material to cover before that. I mean, that's all good, well, and interesting, but that doesn't help you solve discrete math problems.
Okay.
That just gives you a good foundation that now you're comfortable with, and it will help you in other math classes if you pursue them.
Exactly. And isn't that your freaking point? I don't want you guys to just solve problems, I want you to actually learn it.
I do, but
Why wouldn't you teach us that?
because you have to start somewhere.
So teach us about
And if I starting there, working our way to the rationals would take, like, the first 2 months of the class. And that
Crazy.
sacrifices other material.
That's crazy.
Well, that's a lot.
It is a lot.
Like one
But
class period.
that's what you gotta choose to do. So I want to get through as much of that as I can. If we stick with the syllabus, then I intend to go over that kind of material with you as much as I can.
Yeah, that's cool.
Anyways, so yeah, there's nothing wrong with that notation. But you will not have to think about numbers that way for the purposes of this class. I think the author makes a note about somewhere in here. Has you do a little prompt think about that way, but nothing major. So let's do another proof. Proposition 10.5. Let P be the set of Pythagorean triples. Let T be the set equal to that, and T is a subset of P. Okay. So, we need to give a definition of Pythagorean triples first, and then we'll do square. Pythagorean triples. What is a Pythagorean triple? So, a list of 3 integers A, B, and C is a Pythagorean triple provided A squared plus B squared equals C squared. Which should make good intuitive sense to you already.
And they have to be integers, right?
Yes.
Okay.
So a list A, B, and C of 3 integers is called a Pythagorean triple provided that number squared plus that number squared equals that number squared. So what's a Pythagorean triple that you all know off the top of your head?
4 and 5 and
3, 4, and 5.
Oh, 3, 4, 5, there it is.
Here's a Pythagorean triple. That squared plus that squared equals that squared. And there's an infinite number of Pythagorean triples. So, now our proof. You feel like you understand what Pythagorean triple is?
Mm-hmm.
Any questions there? Maybe we'll try another one.
Can there be any?
I
Is it like it doesn't have to be in a row, does it?
Be in a row.
Like 3, 4, 5.
It could also have been 4, 3, 5. That's Pythagorean triple. But it needs to be that squared plus that squared equals that squared. Right. So the sum of the squares needs to be the right hand one.
We've learned these in another math class before.
You've come across I don't know if you come across Pythagorean triples in the sense of a 3-element list.
Not in a list, but we've come across them.
Yeah, you should be familiar with what these numbers are that satisfy this, A, B, and C. Especially working with right triangles. Okay, so Pythagorean triples. Oh, so now our proof. What did we get proof? Prove that P and T be, where's the statement? It has long definitions. Let P equal the set of Pythagorean triples, but how can we write what that is? Let P be the set of all two lists of the form A, B, C, such that A, B, and C are integers, and A squared plus B squared equals C squared, using our set builder notation. You hear that?
Yes.
And let, I'm writing capital L, and let T equal the set keep this in my place, of all P, Q, and R, such that P is equal to x squared minus y squared. Q is equal to 2xy. And R is equal to x squared plus y squared, where x and y are integers. And we're proving T is a subset of P. Then T is a subset of P. So let's make sure we understand these sets. I think you understand the set P pretty well, the set of all Pythagorean triples. So let's make sure you understand this set T. Here's another way to think about it. Picking two integers x and y, okay? Make R equal to that, Q equal to that, P equal to that, then T is a set of those P, Q, R's.
Okay.
Does that make sense?
Yeah.
Okay. Kind of think about it a little bit like a function there. You give it an x and a y and it spits out a P, Q, and an R in that order.
Yeah.
Okay, so we need to show that T is a subset of P. We need to show that any element in T is also an element of P. Right? So and we'll just use P, Q, and R again. Don't let that confuse you. Let P, Q, and R be some element in T.
Why are they confusing?
Huh?
Why are they confusing?
Just because I use the same variable again. I use the same variables every time, instead of coming up with 3 different letters. Okay? So, if we know that that's an element in T, what else do we know about that?
We know those equations are true.
Right, we know that there must exist an x and a y such that P equals x squared minus y squared, Q equals 2xy, and R equals x squared plus y squared. Right? Okay. 2. Then there exists, don't be confused by the fact I'm using x and y again.
Right.
X and y and z, integers x and y, such that P equals x squared minus y squared, Q equals 2xy, and R equals x squared plus y squared. Right? Now, in order to check, in short, what we're saying is all these PQs and Rs are also Pythagorean triples, right? That's what the statement's saying. If T is a subset of P, everything in here is also in here. Or in other words, everything in here is also a Pythagorean triple. So we need to check that this is a Pythagorean triple. We need to check that this squared plus this squared equals this squared. You follow the logic? We need to show that p squared plus q squared equals r squared. That's what it means to be a Pythagorean triple. Yeah. What's his name? Owen Wilson? Is that not what you were doing? Alright. Okay. Then p squared plus q squared is equal to, let's see, what's p squared? It's this squared. Can you do that in your head?
No.
X to the 4 minus 2x squared y squared plus y to the 4.
Right.
I said no.
You do that times that.
You just square this, okay.
You do that times that plus that times that.
Wait, what?
X squared times negative y squared plus negative y squared times x squared.
Just sure.
Okay.
And then that times that.
Okay.
You follow it?
Not really.
Alright, then let's write it out in the simplification real quick. A plus b squared is the same thing as a plus b times a plus b, right?
Yes.
Which is equal to a times a squared, a times b, ab,
Oh, it's
b times
squared.
a, b times b squared. Which is equal to a squared plus 2ab plus b squared. Now substitute. A in our case is x squared, so x squared squared is x to the 4. B in our case is negative y squared, so 2ab is 2x squared negative y squared. That's what we have. B squared, b squared. Follow it now?
Mm-hmm.
Make sense? It's a good thing to book away in your mind to make so that you can do those quickly. So that equals that. So that's p squared. Now we need to do plus q squared. Hopefully you can do that one. Squaring q.
Probably yes.
Yeah, if I want, I'm a teacher. Then we have like terms. We have an x squared y squared term and an x squared y squared term. Here we have negative 2 of them. Here we have 4 of them.
Oh.
Okay? So first I'm going to write my x's. Then I'm going to write my x2, y2 term. And then I'm going to write my y squared. Did you follow that?
Wait a minute.
I combine that positive 4 with that. Oh, sorry.
Yeah, y to the 4.
Good catch. Good wait. Good now? Alright, and then that's equal to
Yeah.
which is equal to
Wait, what the freak? Why would you do that?
That makes sense.
I was showing p squared plus q squared equals r squared. That's how I showed the Pythagorean
That's the
triple.
only mistake
that's
I've
so
ever
cool.
seen.
That's cool.
Why? I thought it was funny.
P squared is literally r squared.
P
No, it's
squared
not.
plus q squared is r squared.
P squared is negative r squared.
No, it's not.
What do you mean? They're literally the exact same thing.
Not quite.
Negative r is
it's the same
negative x
problem.
squared minus y squared.
Instead of
This is positive x negative y. Their squares are different. They're completely different.
No.
P squared is this.
Yeah, which is x4.
R squared
x2,
is this.
y2, y4. Which is
Negative,
the exact same thing.
Positive.
Only not with the pi.
Okay, well
That's what I said.
Okay.
Why are you so rude?
Well, so does this all make sense? P squared plus q squared equals r squared? So that's Pythagorean triple. Right? So there's a nice easy proof that might have looked like it was going to be a pain in the beginning, but turned out to be
Not too bad.
really simple, right? Now let's just write it right out. Any questions about that?
No, sir.
Pretty cool little thing. actually comes from the, well, never mind. You guys aren't that familiar with complex numbers.
Breakdown?
No, we'll do a break when I get to the end of this. Oh wow, this is never ending.
Yeah.
Looks like it's not need a break. Alright. Counting subsets. How many subsets does a set have? So let's look at a particular subset and count how many subsets it has. Let's look at the set 1, 2, 3. How many possible subsets can we make from that set?
3.
More than that.
3?
Oh, subsets.
How many subsets can we make from that set?
1, 2.
7,
I'll give you a hint on one that we can make real easy.
8.
8? How'd you get 8?
Maybe not. Well, either it's 3, 2, 1, 3, 1,
9, 10.
3 and 2, 1 and 2, nothing, 1, 2 and 3.
10. 11, 12.
I might have forgotten one, but it looks like 8.
There they all are. How many did we put up there?
8.
8, right?
Wait, hang on.
Did I miss one? See if you can think of one I missed.
Well, the order doesn't matter, right?
Nope.
Where did I get 10?
So there's no need for repetitions.
8, right?
Yes.
Yeah.
Okay. Well, no, I won't make you do that. So now I'll try to make that make sense to your intuition. Well, maybe I'll ask another question and then we'll fight the intuition. So what if I did the set 1, 2, 3, 4, 5? Oh boy.
Oh, that's a lot.
24.
24. No, more.
Huh?
More than 24.
There's a lot.
There's no formula.
Well, there's a way you can think about it. I mean, there's a reason I can answer that off the top of my head.
Tell us.
32.
Wait. I want to see how you got it.
32.
1 times 2 times 3 times 4 times 5.
Nope, that doesn't give you 32.
Yeah, it is. Oh, no, it doesn't.
So let's think about constructing a particular subset. So I'm making a subset of this thing, right? And I can ask myself over and over again, should I put 1 in the subset, yes or no?
Yes.
Yes, we'll put 1 in. What about 2? Should I put that one in?
Yes.
Well, let's not put that one in. What about 3? Should we put that one in? Sure. No 4, no 5. There's a possible subset, right?
Yeah.
This subset containing 1 and 3. So for every element in there, I have 2 options. Should I use it or should I not use it? Right? So I have 2 options whether or not I want to use 1. I have 2 options whether or not I want to use 2. 2 options, 2 to the 5. Wonderful.
The other one's just
2 to the 3.
Wait, 2 to the 5 is 32?
Yeah.
See, I freaking had that. All I did was, instead, I squared 5. And minus 1. That's why I said 24. Good thinking, Sony. Good job.
Oh, I was wrong.
Oh.
And I don't know why the minus 1. But anyways, so there's a way that you can think about. For each subset you can create, you can choose, do I want that element or not that element? Do I want that element or not that element? So there's your intuition for how to think about how to count all possible subsets.
because there's 2 options for each one.
For each element in there, you can think out 2 options. Do I want it or do I not want it? That's the way I think about it. I don't know if the author walks through different intuition. I recommend reading it to see if he does, because maybe he gives you a better way of thinking about it than I do. That's just my thought process. Now we have, make sure I get this notation right. Oh, we don't define the power set yet. Okay, so all the author says in general, well, I don't know if he already introduced this notation, I missed it. So, notation. When we use the absolute value symbols around a set, that means the size of. So the size of this set is 5.
Why do you do that?
Absolute
We
value.
just decide that.
It's common notation for like, none of you guys have done trig, but it's the same notation you use for like the size of a vector, the length of a vector. It's similar notation. The absolute value of a number, you kind of think about how long the number line is from 0 to that number. So it's common notation for the size of. So in the context of sets, it means the size of the set. Okay? So if I have a set A, then the question is, how many possible subsets can I make of A?
You take, it'd be 2 to the power of the absolute value then.
There you go. So if I have a subset A, and I want to know how many possible subsets can I make for A, the number is 2 to the power of the size of A. 2 to the power of the size of 5, or 2 to the power of the size of this, which was 5 in this case. 2 to the power of the size of this, which was 3 in this
Is
case.
there no?
It doesn't make sense? Okay, so let's do one more.
Oh, hang on. Because you think of A as a set, right?
Yeah, A is a set. So if I say A is equal to the set 1, 2, and I want to know how many possible subsets can I make, we know the answer is 4, right? That's 2 to the size of the set containing 1, 2. Which is equal to 2 to the size of A, which is equal to 2 to the 2. All those are the exact same thing, if A equals a set.
Right.
Does that make sense?
Is there a notation for like all of the subsets possible in the set?
Yeah, that's called the power set. So that's the next notation we're going to come across. And let me see the author's notation for it.
Wait, what was your question?
Saying, is there a way to write all the subsets of this set? Like as a notation?
Okay, that's how this often does it. Sorry. Some books do it differently. So some people do the power set. They do like a weird slanted P with like a big P like that, the power set of A. That would be equal to all subsets. The way this author does it is he does 2 to the A.
Okay. 2 to the absolute value of A?
No, that means that's a number. This is a number which is 4. This is a notation for all the possible. Let me make sure I did that right. Pretty sure that's right. 2 to the A. Yeah. I thought he did the fancy P. Maybe he'll introduce that later.
He says the absolute value of 2 to the A.
No, that's the size of it.
Oh.
He says the size of this set is equal to this. The size of the power set of A is equal to this. But he's using, so let's say A equals a set 1, 2. Then he's using 2 to the A is equal to the set contains the empty set, contains the set containing 1, contains the set containing 2, and it contains the set containing more 2. So make sure you understand what the power set is. It's the set of all possible subsets. There's a possible subset of A, 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 all wrapped up in a set. And the
That's
size of
2A.
this set is 4.
That's just 2A.
2 to the A. The reason that they do this is that gets into functions, and we're not there yet. It's a common shorthand of function notation where this is the domain and this is the range. And remember where 2 is the set containing 1 and 0?
Yeah.
This is where it might be useful to bring this back up. So another way of writing that is, this is shorthand for all the functions from A to 1 or 0. 1 means include it, 0 means don't include it.
Oh. Okay.
So another way that we capture the same information is rewriting this would be
Oh.
something along the lines of, let's see.
Sorry, yes/no.
So is there
Yes, exactly. Yes/no for a particular element. I won't write that.
is there ever
We'll
going
wait till
to
we
be
get to that motivates the 2 in there though.
if you're gonna use like 3 or 4 instead of 2, any other number besides 2?
Not for counting subsets, because the notion is 1 means include the element, 0 means don't include the element. We don't have a third
Because
case
there's only two
for
choices.
subsets. Right? That's what I was trying to capture here.
Uh-huh.
We either include it or we don't. If it maps to 1, that means include it. If it maps to 0, that means don't. And we take all the possible ways that we can map that, and it's a similar idea. Well, it's the same idea, just expressed using different notation. So that's where the 2 comes from, and that feels like the most random, arbitrary thing that you've ever seen.
No, it makes sense. I mean, we just talked about that, but I'm just wondering if every time we need to have more than that.
You would use this notation in other ways, just not for counting subsets.
Okay.
And I don't think that the author will use that notation again in this class. The only other place I've seen that is in
2 to the
more
a
units math textbooks.
has nothing to do with exponents. It's just a notation.
It's just a notation, but the reason it's nice is because it just so happens that when you take the size of it, it's that. That's what's nice about it.
So why do we write it like that? It makes it look like an exponent. Why not write it 2 sub a or something?
Well, we liked that this and this are the same thing. That's nice.
How are they, what are you?
The size of this set, 2 to the a, the size of this set
Because 2 to
is
the
the same
A-
thing as 2 to the power of the size of a. So we
Oh,
like
that
the
makes
fact that
sense.
that's true.
With the eggs
But you can't really.
So that's what makes the notation convenient.
So what does 2 to the a? Well,
What does that mean?
I'm saying if you think about it in terms of exponents, how do you?
It's not an exponent.
I know, but all right.
This is an exponent.
That's an exponent.
This is not an
The 2 eggs are
exponent.
different.
So,
they represent different things.
Why does it change?
But the fact that the size of this equals 2 to the power of this is convenient. So you could remember, because now this is just a number. Once I put the absolute value on it, it's a number. And that number is equal to that number. And the fact that you can do that is convenient.
But how do you solve the first number without using the other side?
I don't mean by solve this.
So you're saying you make it a number. How do you find out what that number is? Without using the other side of the equation.
Well, I guess you could count it if you wanted.
The only thing, the thing I'm struggling with is,
Keep in mind what these two numbers represent. This number represents the size of this set.
right, so
This number represents 2 to the power of the size of this set. Or
right,
this set.
that makes sense.
And those two numbers are equal.
That part makes sense. So what I'm wondering is why do we notate the 2 to the a the way that we do instead of saying 2 sub a or 2 something else?
Well, why you use particular notation is probably going to come down to historical reasons. It's just common to have some range, some domain as a shorthand for all the functions from here to here.
And it's just written like that?
That is a notation.
Okay.
But it doesn't come up that much.
Just wondering how you distinguish that from exponents, because they look at
Well, you come across this kind of stuff all the time. I mean, you have 1 plus 1, we use parentheses that way. You represent a point 1, 2, we use parentheses that way. We have 4 to the negative 1, we use negatives that way. I don't know. I mean, you just have notation being used in different ways.
Okay, anyway, yeah, that's all I guess.
So, I mean, why is notation the way it is? The answer is typically some author in the past used it that way, and they published a book using it that way. And since they were the first one to speak on the subject, their notation continued to be used. It is a common way that notation gets established. Another one is we have the negative sign, and we also have the minus sign. Those aren't the same thing. And you infer from context what's meant. Right? So, you're typically able to infer from the context what's meant.
Yeah, I guess so, that makes sense.
Alright. So that's the power set. And that finishes that. So you can go on break, and when you come back, we'll do the last section.
Okay.
I didn't make a test.
Dang it.
Sorry about that. Didn't have time.
It's alright. Can't meet your person this week anyway.
Your person.
Yeah.
Who's your person?
Tutor. Who's gonna help me with that this week?
You have someone helping you? That's awesome. Who is it?
Oh, it's just.
Is she doing that for credit of some sort? Cool.
She just loves me. here every Tuesday.
That's a good idea.
How's your baby doing?
She has stomach problems, which is a pain, but other than that, nice and healthy. Yeah, like she gets bubbles easy, so when you're feeding her, like 5 minutes to it starts hurting her to keep eating, so you have to stop and burp her. So sometimes it can take like a little over an hour just to feed her a bottle.
Yeah, that's how my little sister Erin was.
Yeah, apparently it's a common Timpson issue, so.
Oh, that's right. Do you tend to do small homeworks on test days?
We cover less material on test days, but you turn in a lot of homework on test days. It's the day after test that you turn in a little bit of homework, or the week after.
Right. Last week we had a test, and then we had time to homework.
Right. Yeah, that will be the case. Never cover more than one section on test day. Or maybe there's one instance of that. I don't know.
Where is the green jacket?
What is the upside down?
For all. Or for
Upside
each.
down A's, backwards E's.
That's right.
I was teaching us math, my friend.
Okay, so let's start going over quantifiers and then we'll go from there. Okay, quantifiers. There's two quantifiers where I don't know if I've already introduced them to you. I have a habit of writing them. But the two quantifiers we're going to talk about is there exists, represented with a backwards E, and then for all, or for each, or for every, which is represented with that upside down A, as he called it. So, let's go over proofs, seeing these in actions, now that the authors finally introduced them. proof that there exists an integer such that x is even and prime. How would we prove something like that? Observe 2 is even and prime. So notice that there exists means there's at least one case where it's true. So we showed that there's at least one case where it's true. We're done.
So that's so confusing, because with this, you prove one case, and then with this, you have to freaking set up a formula of it.
Yeah, you have to prove it for all cases. So now let's go over the other one. For all, represented with that symbol, let's do a case with that. Let A equal the set of all integers such that 6 divides x. Then for all x in A, x is even. Another way you can think about this is we're showing that this set is a subset of the evens. For all x in A, x is even. So now let's prove that. Let x be in A. Then 6 divides x. Then there exists some integer little a such that x equals 6 little a. Then x can be written as 2 times 3a, which means 2 divides x, which means x is even. So this case we need to show that for every single integer that's divisible by 6, it's even. Here we need to only find one example of an integer that is even and prime. There exists means we're looking for one. For all, or for each, means we need to handle every possible case. Right? Let's use it in just common language. I say that there's a teacher in this room. That means at least one person in this room is a teacher. There exists a teacher in this room. At least one person in this room is a teacher. If I say for all people in this room, that how's I'm trying to say that weird. If I were to say everyone in this room is a teacher, the notation we would use is for all x, where x is a person in the room, a member of the room, use R to mean a person in the room, sorry. X is a teacher. This statement isn't true, right? So there exists a person in the room where x is a teacher.
That makes so much sense.
So there exists a person in the room. There exists some x in R, if R is a set of
There's
people in
at
this
least
room,
one, and then
such
all.
that x is a teacher. But for all x in R, for every person in the room, x is a teacher is false. So this is a false statement, this is a true statement. Right? You see the difference between the two? And so when we prove a there exists statement, we only need to find one case where it's true. If you are trying to prove that there is a teacher in the room, you just need to find one person in the room that's a teacher. If we want to prove a for all case, for all x in A, x is even, we need to handle it for every possible x. We need to say pick any x you want, here's how you show it's still even. Notice we couldn't use particular numbers for x in this case, where we could up here. So the only way to prove this statement is true is to check every person in the room and make sure they're a teacher. Does that make sense? The difference between those?
It does. Yes. Wait, why did you just erase those?
Because they weren't part of the text.
Well, they help me.
Alright, so now let's go over negating quantifiers. Because negating quantifiers can be kind of counterintuitive. So, there is no integer that is even and odd. Okay? What is that the not to? That is the not to this statement. There exists an integer, x, such that x is even and odd, and we're saying the not of that. There is no integer. There is not an integer that is even and odd. Not, there exists an integer, x, such that x is even and odd. I need you to make the connection between these two. See how they're saying the same thing. And then we'll work with how it's weird, the connection between these two. So let's look at this one. Not all integers are prime. That means not, for all integers, x is prime. For all integers, x is prime. Do you see how this and this are the same? Kinda? Alright. So now let's look at what those statements mean in terms of quantifiers. So let's rework this statement and rework this statement in terms of quantifiers. Sorry, this is kind of jumping. So we've got this is connected to this, and now we're going to rewrite the statement down here using the for all quantifier. That's the same thing as for all x in z, not x is even and odd. And then this one's connected to this one's connected to this one. We can rewrite this as there exists an x in z where not x is prime. Make sure these make sense to you.
Wait, shouldn't that be for all? Sorry, there exists.
Now, so let's take on the statement one more time. There is no integer that is even and odd, right?
Okay.
That's the same thing as not all integers are even and odd, right? There is no integer that is even and odd, sorry. For all integers,
Alright, for all integers, there's not one that's even odd.
let's walk through the work. What you're saying is right, but let's see it here. There is no integer that is even and odd is the same thing as not there exists an integer that is even and odd.
Oh.
There is no integer that is even and odd is the same thing as not there exists an integer that is even and odd. Okay?
That makes sense.
Now I'm going to distribute this not. And with just these statements, and I'll show you how to do it generically, but I think seeing examples helps first. So I'm going to rewrite, you see how this statement and this statement capture the exact same information. Sorry, I should have mixed these together. I should have done this one all the way through and then the next one. So we're jumping from here to here. You see how that's the same. Now see how this and this are the same. That means that for all integers, it's not true that x is even and odd.
Okay, that makes more sense.
Okay? So now let's mess with this one. Not all integers are prime is the same thing as not for all integers x, x is prime. The statement for all integers x, x is prime is not true. Not all integers are prime. You see how this and this capture the same information? And then we can distribute the not. Not all integers, not for all integers x, x is prime, is the same thing as there exists an integer that is not prime.
Okay.
So the way you have these in general is, I say there exists x, some statement about x, and for all x, some statement about x. So that's when you see the quantifiers in general, anytime you see them. Here we say there exists an x, some statement about x, x is even or prime. So here's how you see it come up in context. These symbols in general, okay? And then when I say not there exists x, statement about x, is the same thing as for all x, not statement about x. Similar here. Not for all x, statement about x is equal to there exists x, not statement about x.
Wait a minute.
So let's look back at this notation real quick, and we'll just pick our own statements as we go. So let's make our statement, there's a teacher in this room. There exists an x, such that x is a teacher in this room, right? That's how we might use this notation in general. You good? Okay, so now let's look at this. Not there exists x, x is a teacher in this room. Not there exists a teacher in this room, basically, right? Not there exists x, such that x is a teacher in this room, is the same thing as for all x's, x is not a teacher.
Huh.
If there does not exist a person such that they're a teacher, that's the same thing as saying for all persons, they are not a teacher.
Oh, that makes sense.
Let's look at this one again. I don't know, what statement should we pick?
Teacher.
Likes pickles. So we'll think about x is a set of people, and the statement is likes pickles. For all x, for all people, x likes pickles. Every person likes pickles is what this is saying, right? So not for all people, they like pickles. What's the not of that? There exists a person that does not like pickles.
Oh.
The statement
That
S
makes so
is likes
much
pickles.
sense. Okay, where have I learned this before?
You come across this in what is
So
called the
geometry.
contradiction in geometry.
Yeah.
And it's probably not a bad idea to introduce this concept in this class. I was going to introduce it with logic, but the author didn't put a lot of pressure on it, so I did. But we can have this conversation anyways, because it's kind of misunderstood. Going way, way, way back, we said a statement is either true or false, right?
Right, yeah.
And we said that the not of a statement is a contradiction of a statement. Right? So if a statement is true, then its contradiction is false. And if a statement is false, its contradiction is true.
Right.
It's called the law of contradiction. If a statement's not true, it's false. If a statement's not false, it's true. And so a way that we can do proofs is we can prove that a statement's contradiction is false. Therefore, the statement is true. Right? Now, there's a difference between contradicting statements and contrary statements. Two statements are contradicting means one of them has to be true, one of them has to be false. Those are contradicting statements. Contrary statements are both statements can't be true. Let's think about contrary statements for a second. Donnie is wearing a plain black shirt. Donnie is wearing a plain white shirt. Those are contrary statements. They can't both be true. I might be wearing a yellow shirt. So they can both be false, but they can't both be true. Those are contrary statements. Contradicting statements are Donnie is wearing a black shirt. Donnie is not wearing a black shirt. One of those two statements has to be true. So the not gives us the contradiction. So a common example is, let's see, all...
Hang on. Neither of those statements have to be true.
Donnie is wearing a black shirt. Donnie is not wearing a black shirt. One of those statements has to be true.
No,
Am I wearing a black shirt?
that doesn't matter.
Okay, let's pretend I was wearing a yellow shirt.
A yellow.
If I'm wearing a yellow shirt, am I wearing a black shirt?
No.
I'm not? I'm not wearing a black shirt. You're saying the statement, I'm not wearing a black shirt, is true. You can't say that a statement is not true and not say its contradiction is
Oh,
true.
that is true, huh?
By saying it's not true, you're saying the contradiction is true. The not of a statement is its contradiction. So the question is, how do we not some statements? So let's pick one. All cats are black. Contradiction of that is what?
There's a cat that's not.
Is it all cats are not black?
No. There's just a cat that is not black.
There exists
Wow, you actually wrote that out.
a cat. That's exactly right. That is not black. So let's look over this in terms of our quantifiers. We're saying for all x in the set of cats, x is black. Right? For all x in the set of cats, x is black is this statement right here. Right? Now let's look at its contradiction, which means not it. Using our rule here, not all x, statement about x, means there exists not s. So that is equal to, there exist x in C, not x is black. See how that's exactly what you did? The contradiction of, for all cats x, x is black. The contradiction of that is the same thing as there exists a cat such that the cat is black is false. Not a cat is black. So that and that are contradicting statements. And that's what these rules are giving us. How do you distribute the not? How do I get the contradiction of the statement? Take this statement, for all x and C, for all cats, x is black, and now not it. How do we take its contradiction? It's not.
All cats are not black. That doesn't make sense.
No, this one isn't the contradiction.
That's what the top
This one is bad.
Okay, but that's what the top one is saying, isn't it?
No,
That's
this
what
was
the top
is
one
saying
is saying.
not. For all cats, a cat is black.
Exactly.
It's saying not that. It's saying the contradiction of that.
Meaning not all cats.
Which is the same thing as there exists a cat where the cat is black is not true.
So
This means
the
contradiction
top
of
one, the top
not.
one is specifically not saying all cats are not black.
So this one, this statement is inside the parentheses.
Right.
The not of that
Not
statement
that.
is not this, it's this.
That is so weird.
So that's how you distribute a not. If you want to take the not of a there exists statement, here's how you do it. If you want to take the not of a for all statement, here's how you do it. You just barely took the not of a for all statement and you did it like this. And yeah, you can do this in geometry. When you were taking the contradictions of statements, you were distributing knots.
So
And that's it.
okay, hooray.
So feel free to get started on your homework, look through all your questions, find the ones that you think are going to be the most challenging so you can ask me. Turn off the lecture.